All right, let's talk about the stuff that makes up, well, everything. The phone in your hand, the car you drive, the bridge you cross every day. Our whole world is literally built out of materials. But here's the secret. These materials aren't just found, they're designed. Today, we're going to pull back the curtain and uncover the hidden science that gives these everyday things their incredible strength and, their unique personalities. Let's get into it. It all kicks off with a really simple question. You've probably done this a million times. You take a paperclip, you bend it into some weird shape, no problem. But if you drop a heavy cast iron skillet, crack. It might just shatter. Why? I mean, they're both metal, right? Well, the answer is hiding deep inside their atoms, and that's exactly where we're headed. So here's our game plan. First, we'll talk about what makes materials different in the first place. Then, we'll dive into the secret blueprint of metals. After that, we'll see how engineers can literally change a metal's personality. And finally, we'll put it all together to see how we build with atoms. Okay, first things first. When an engineer looks at a chunk of metal, they don't just see metal. They see a collection of properties, kind of like a unique personality that tells them exactly how that object is going to behave out in the real world. And this gets us right back to our paperclip and our pan. That paperclip, it's what we call ductile. It can stretch, it can deform, it can be pulled thin like taffy into a wire without breaking. But that cast iron, that's brittle. It fights against changing its shape. And when you push it too far, it doesn't bend, it breaks. Same material family, two totally different personalities. Now, engineers like to keep things organized, so they basically split these personalities into two big groups. You've got mechanical properties, that's stuff like strength and ductility, which describe how a material handles being pushed, pulled, or twisted. Then you have physical properties, like density or melting point, which are more about its basic inherent nature. Simple rule of thumb, if you're applying a force, it's probably mechanical. Let's dig into a really important physical property, density. In the world of engineering, we measure this with something called specific gravity. It's really just a simple way of comparing how dense a material is compared to water. And here's the key number you gotta remember, 4.5. If a metal's specific gravity is under 4.5, we call it a light metal. Over 4.5, you guessed it, heavy metal. And this is where it gets kind of wild. The range is just enormous. On one end of the spectrum, you have lithium, with a specific gravity of just 0.53. That's so light, it would literally float on water. Then, way over on the other end, you've got osmium, one of the densest things on the planet, with a specific gravity of 22.56. That is more than 22 times heavier than the same amount of water. Just imagine holding that in your hand. What about handling heat? Check out this number, 3,410 degrees Celsius. That's the temperature it takes to melt tungsten. To put that in perspective, the aluminum foil in your kitchen gives up at just 660 degrees. This is exactly why tungsten was the perfect choice for the tiny filament in old-school light bulbs. It could glow white-hot without turning into a puddle. And what about moving electricity? Now, you might think it's gold because, it's gold. But silver is actually the champion conductor. So why aren't the walls of your house wired with silver? Well, look at number 2, copper. It's an amazing conductor, and it's way, way cheaper than silver. It's the perfect sweet spot between performance and price. So what's the secret sauce? Why are metals so good at conducting electricity and heat anyway? It all comes down to something called free electrons. Just picture a sea of tiny charged particles just zipping around inside the metal's structure, totally free to move. When you apply heat or an electric current, they're ready to carry that energy right down the line. Okay, so we've covered the what, the properties that give a material its personality. But now it's time for the really cool part, the why. To figure that out, we have to shrink ourselves down, way down, and take a look at a metal's secret atomic blueprint. You might imagine the atoms inside a piece of metal are just a random, jumbled mess, but that's not it at all. They're actually stacked in these incredibly neat, organized, repeating patterns. The best analogy? Think about how oranges are stacked at the grocery store to make a perfect, stable pyramid. That repeating pattern of atoms is what we call a crystal lattice, and the exact way they're stacked changes everything. Two of the most common patterns are called body-centered cubic, or BCC, and face-centered cubic, FCC. In a BCC structure, there's an extra atom wedged right in the middle of the cube. This makes everything tightly interlocked, and the result is a metal that's really strong and hard. The FCC structure, though, is a little more spaced out. It allows layers of atoms to slide past each other, which gives you a metal that's malleable and ductile. And here's the proof. Check it out. The strong, hard metals, like the tungsten we just talked about, and the iron in that brittle skeleton, they're BCC. And all those ductile metals, the ones you can bend and shape and pull into wires like aluminum, copper, and gold, almost all of them are FCC. The atomic blueprint directly creates the material's personality. It's a direct link. So if a metal's personality is basically locked in by its atoms, does that mean we're just stuck with whatever nature gives us? No way. This is where engineering gets really creative. We get to be like master chefs, using special recipes to cook and mix materials, creating totally new personalities. One of the most common recipes is called alloying. It's really just what it sounds like. You're mixing different metals together, or maybe adding in some other elements to create a brand new material. The whole point is to take the best properties from each ingredient and make something even better. And you've definitely seen alloying before, even if you didn't know the name for it. Pure 24-karat gold, it's actually super soft. You could probably bend it with your hands. So to make it strong enough for a ring you can wear every day, jewelers mix it or alloy it with other metals like copper and silver. That's how you get 14-karat gold, a much harder, more durable material. That's alloy. Now, besides just mixing things together, engineers also cook metals. This is called heat treatment. And we're not just talking about sticking it in a fire. This is a super precise, carefully controlled process of heating and cooling. The whole goal is to force that internal crystal structure to rearrange itself and, in doing so, completely change the metal's properties. Take tempering, for example. It's a classic recipe for making steel tough, like for a sword or a high-quality tool. First, you heat the steel way up. Then you quench it, plunging it into water or oil to cool it down incredibly fast. This locks in a structure that's super hard but also super brittle. So the final step is to gently reheat it, or temper it. This step eases the stress inside the metal and gives it that perfect balance of hardness and toughness. And you know what? You can be a materials engineer without a giant furnace. Go back to that paper clip. If you bend it back and forth right in the same spot, you can feel it getting stiffer, right? It gets harder to bend. That's a real engineering process called work hardening. Just by bending it, you are physically changing its properties. How cool is that? All right, let's bring it all home. We've gone from a simple paperclip all the way down to the atomic level and then all the way back up to the recipes engineers use every day. So what's the big takeaway? Here it is, the engineer's toolkit in a nutshell. We use properties to talk about a material's personality. We know that this personality comes from its secret atomic blueprint. And this is the most important part, we can change that blueprint with recipes like alloying and heat treatment. Which leads to the single most important idea. The materials that built our world, they aren't just things we dig out of the ground. They are designed. And of course, to keep all this complex science straight, you need some clever tricks. For instance, engineering students in Korea sometimes use this little mnemonic to remember the common ductile, or FCC, metals. It's a fun little reminder that engineers all over the world are finding ways to master this stuff. For centuries, we have been designing and perfecting the metals that built our entire modern world. But the science is always moving forward. Right now, people are designing self-healing plastics, impossibly light composites for space travel, things we can barely even imagine. And that really leaves us with one big final question. What incredible new materials will we design to build the world of tomorrow? Thanks for joining us.